All right, good morning. This is scenario 2 for two sample proportions. And this is your stats sensei, Mr. Spensey, and we're along for a ride and hope that this goes well. An automobile manufacturer randomly assigns cars to two distinct assembly procedures. Hey, we have two separate groups. That's interesting. That tells me I'm probably working with a two sample means or two sample proportions. In a sample of 355 cars, coming off the line using the first procedure, there are 28 with major defects, while a sample of 500 from the shows 32 defects. Hey, we didn't have an average number. So since it's not an average, this can't be a test for means. But I could set this up as a ratio, all right? And because I can set them up as a ratio, this is a proportion. Ratios are proportions, as are percents. So this tells me I'm working for a two proportion test. And they want to know whether or not there's a significant difference in the number of defects. So P1 is the true population proportion of cars with defects with the first assembly procedure, and P2 is the true population proportion of cars with defects with the second assembly procedure. So what we are saying is the null is they equal. There's no difference. P1, the true population proportion of cars with of defects with the first assembly equals the true population proportion of cars with defects in the second assembly. And obviously here we're just saying they're not the same. Please remember, we can always write this as a subtraction. So P1 minus P2 equals 0. The alternative, P1 minus P2 does not equal 0. One thing to keep in mind, we're working with a not equal to, so at the very end, we know we're going to have to be doing 2 times the probability statements. So random assignment. Hey, we were randomly assigned. Awesome. Make sure you, if they are randomly assigned, make sure you say that. Make sure that you say that that's given. Don't use random sample if it's random assignment. They will ding you. They'll knock you from full credit to a partial. All right. So random assignment was given. Reasonable summa independence, as the treatments were randomly assigned and one assembly procedure should not impact the others. That seems reasonable to me. We need to make sure our sample size is large enough. Well, they tell us the first one out of 350 cars, there was 28 defects. So 328 defects, well, 28 is greater than 10. And then 350 minus the 28 is 322, and that's greater than or equal to 10. And over here, we had 32 out of 500, but 32, which is also greater than 10. And then 500 minus 32 is 468. So both samples are large enough to use the normal approximation. Okay. I did not test the n is less than 10%. That was an error. So we need to go back and let's look at that since we don't have that there. What we should be saying is 350 divided by 0.10 and 500 divided by 0.10. This is 3,500. This is 5,000. Reasonable to assume that there are more than 3,500 cars being eligible to be made with this method. There's at least 5,000 cars eligible to be made with this method. All right. So that should have been there, but it's not. All right. So because we're working with a hypothesis test and we're working with proportions, we have to pool. So we have to use the pooling equation, which is x1 plus x2, n1 plus n2, which would be successes plus successes over both sample sizes. In this case, this is the number of defects for 1 and the number of defects for 2. Well, the number of defects on 1 was 28 and on 2 was 32. And we end up getting a P combined of 0.0706. Now, please note, some things are going to say P for P pooled, all right? And We also know that P1 is 28 divided by 350 or 0.08. P2 is 0.064. So right there, I see that P1 is, these two are not the same values. The question is, are they different enough to be statistically significant? Is it statistically significant? So we're going to plug in, and this is P hat 1 right here. This is P hat 2. So this is my estimate of the number of defects for using method 1. This is my estimate for the defects for number 2. And then my combined 0.0706, 1 minus that here over N1. P hat combined, 1 minus that over my sample size for 2. And we're going to go ahead and start plugging that into the calculator. Stat, test, and 2 proportion Z test, which is number 6. And in this case, we had 28 defects out of 350 on the first production line. On the second production line, we had 32 defects out of 500, and we're running a two-tailed test. I end up with a positive Z score. So when I write my Z, this part right here, I need to have a greater than. All right, so right here, I need to have a greater than. So 2 times the probability is greater than Z is 0.8963, which is what we got here. The calculator gave it that to us. This first P is our P value. So our P value is 0.3700. And just in case we wanted to check, P hat 1, 0.08, P hat 2, 0.064. And then we have P hat without a notation. That's P hat combined, right? So this last one here is our P hat combined, all right? So it actually calculates it for you, but you still have to show this work, all right? So this is your work shown. Now our P value is 0.3700. It's greater than alpha, so we're going to fail to reject. All right, so if we're going to fail to reject, that means I believe this, which is basically saying the true population proportion of cars with defects in assembly procedure 1 is the same as in assembly procedure 2. In other words, there's no difference. So our P value is 0.3700. We fail to reject the null. There is not sufficient evidence that alpha equal 0.10 to suggest the true population proportion of defects has changed from the one assembly method to the other, or is different, right? So has changed or is different. From our study, both assembly methods appear to reproduce the same proportion of major defects. The cars will fail and people will die, but at least we'll know that the proportion will be the same regardless of the assembly method. Okay, that was me being a jerk. Easy to do sometimes. I hope this helps. Look forward to seeing you in the next video where we look at an AP release test question on proportions and how they try to relate one sample to 2 sample. This is your Stat Sensei. See you on the next one. Thank you.